Hello, everyone. Welcome to ActInf Lab. This is ActInf Lab ModelStream number 3.1. It's May 27th, 2021, and we're here with Tim Verbelen and Ozan Catal. Today, we're going to have a model stream on some of their recent work on learning generative state space models for active inference. We're going to have a presentation followed by some time for question and answer. So please feel free to write any questions in the chat and we will get to them in the conversation. So thanks again to Tim and Ozan for joining us today. We're really looking forward to what you have to share. So please take it away and thanks again.
So thank you, Daniel, for having us. So I'm Tim Verbelen, and together with Ozan Catal, we will talk a bit on our paper on learning generative state space models for active inference. So we are both researchers at IMEC Ghent University in Belgium. If you want to know more about what we do, you can read about it on our blog or follow us on Twitter under @thesmartrobot. So before we dive in, maybe a short introduction on what we do, what our goal is. So basically, we want to build intelligent robots. So in our lab here in Ghent, we have a pretty big, pretty large space where we have some room for robot manipulators on the one hand, but also driving and flying robots on the other hand. And we typically attach all kinds of sensors on these things, and then we want to process the sensor information and infer some useful actions for these things. And of course, active inference is a cool methodology to try out and to further investigate. And it's in this context that basically this work is being done. So why would you bother learning the state space? So if you look at active inference papers from the recent years, then typically you will find a figure like the ones that are on the slide. So you have this figure of what is the kind of environment that you're modeling, that you're investigating, and then a whole description on how the model should look like. So you define the state space, and then possibly, or in the case of discrete state spaces, you define the so-called A, B, C, and D matrix that defines the likelihood model. So what is the likelihood to see a certain observation when you are in a certain state, or what are the transition models? How do you transition from one state to another, and so forth. And recently, while we were doing this research, we saw some other people also thinking about, can we do more learning using these kind of novel deep learning techniques in these active inference methods? So you had, for example, Kai Ulshofer, who said who proposed to basically learn kind of a state space for the mountain car, but then still he needed to explicitly encode some of the environment information in the state vector. There was also some work from Baron Milic, who basically did some learning, but more on learning the policy rather than the state space. So he basically used Markov decision process with small state spaces where you could basically just deal with the raw state space, the raw observations that the environment gave you were basically suited as a state space, and he would then investigate how to learn the actions given these states. But so our work is basically on what if you don't know the state space? What if your observations are high dimensional and you cannot really use these directly as your state space? How do you define the model? How you can come up with it? And maybe as a concrete example, suppose we have one of our driving robots in the lab. So this is a first-person view of the robot. This is the kind of observation that you get is just a square of pixels. And then, what is your state space in this case? It might be an XY position on the map, that might be something relevant for a robot as a state. It might also be, watch out, you're approaching a cable gutter, so there might be a bump. That might also be something useful. Maybe the items that are stored in the racks are relevant for whatever task you have, so that might also be part of the state space. Maybe there are human workers that walk around, and you also need to model these. So depending on your robot and the use case you have, the task at hand, and what can happen in the environment, it becomes non-trivial to define kind of a concise set of states that you want to track, let alone that you need some model that models this. Like, how do you get from pixels to your XY position? So there are certain methods in robotics that do part of these things, but none of them really just figure out what is the complete state space that you need for whatever you want to do, and especially not in kind of an active inference setting. So before we go into our methods, I'll briefly talk about active inference. Probably most of you are already familiar with the topic, but I'll just rehearse some of that stuff, even if it's just to get accustomed to our way of notation, let's say, because everybody has his own notation, and at least it will put us all on the same page for the next part. So it all starts with having an agent that needs to interact with the environment, and the agent is assumed to be kind of separated from the environment from the so-called Markov blanket. So on the one hand, the agent can perform actions. These actions, these will impact the environment, which is kind of a generative process that has some hidden states, and that provide you, given your action, it provides you with some sensory observation. So in this case, an action could be for the robot to drive around, to put some current on the motors, and an observation could be some pixels from the camera. And then the goal of the agent is to build a generative model where he has his own, he builds his own state space, basically. He derives how actions have effect on the states, and how these states then would generate these observations. And so the question is, how can we build a generative model that actually comes up automatically with kind of a proper state space to learn this model? So basically, the generative model then looks like a POMDP, a partially observable Markov decision process. So it just means that we assume that a state at a given time step, it only depends on the previous state and the action that you were doing. And each state gives rise to a certain observation. And so then we end up with the so-called free energy principle, that basically what we want to do is we want to build a model that maximizes log evidence. So here you see the formula for the free energy, and you can unpack it in several ways. So the first way is basically by stating that minimizing free energy is actually maximizing the evidence lower bound, let's say. And if you're at this free energy minimum, then basically you have your approximate posterior that this is actually equals to your, or very close to your true posterior. But then the third line is basically what we typically use for optimizing our model, which is basically, on the one hand, a complexity term. You want to have your states explain the way as simple as possible, whereas you want to have the highest accuracy to predict whatever you're observing. And so in this case, our variational approximate posterior is something that maps observations and actions into inferring your current state. But what about the future? So in the past, you basically knew which actions you were doing, and you saw the observations that came in. So you could kind of infer which states would have given rise to the observation. So that's basically the free energy of the past. But then in the future, things change a bit because now you don't know what you will observe, and also you have to select the actions you will do. So the actions, we will basically denote them as being generated by so-called policy. But in this case, the policy is basically just, what is a certain sequence of actions, basically. And you now have to create some expectations, not only on future states, but also on future observations. So which states do I think I will visit by doing some actions, but also what kind of observations do I think that I will see if I visit these states. So then the free energy becomes the so-called expected free energy. And again, you can unpack this thing as follows. So basically what happens is, again, you have on the one hand your the log probability of your posterior model minus log probability of your generative model, and now the difference is that that you don't know yet the observations in the future. So you condition it on the policy, so everything will depend on the actions you will do, and you also have to take the expectation over all kinds of outcomes you expect. And then going to the second line, you basically make the move that after, if your model is sufficiently trained, then basically your true your approximate posterior will be very close to the true posterior, and this then basically allows you to rewrite the final term. Well, I see now that I wrote it in a different way, but you can rewrite this either as an information gain on your states and moving towards preferred outcomes. But you can also rewrite it the way read it here, where you basically state, okay, at some point in the future, I will visit some states. So this is this log P of S star given the policy. And you basically replace this by some prior belief that regardless which policy I'm actually choosing, I believe that some point in the future I will realize my preferences. So that's why you lose the conditioning on the policy in the last equation. So this then basically becomes a KL divergence that says, okay, I want to find the policies that actually bring me close to the states that I prefer, that I like to be into. And then on the other hand, you have this ambiguity term that says, okay, what I don't like is to visit states that can give me like any observation that I cannot predict. So I don't like these ambiguous states where I don't really understand basically what's happening. And so that brings us to the whole active inference scheme. So at each time step, you basically evaluate your expected free energy for each of your policies. And you then basically assume that you will choose the policy that will actually minimize your expected free energy. So you take the softmax over minus G, and you also weigh this with this gamma parameter, which is just like the precision. So if you have a high precision, then basically you will have a very peaked output of the softmax function. So the softmax will basically become a max. So you then definitely choose the policy with lowest expected free energy. If you relax the precision a bit, then basically you allow for some more randomness in the system. And then basically you end up inferring the next action according to what is the next action that I should take according to this policy. But so for it follows, the action selection given the policy is basically just a deterministic mapping. So the policies are just like certain sequence of actions. So given once you choose the policy, the action is basically fixed. But in theory, you could also make this a probabilistic mapping. So let's now go to the real interesting part of the work is how do we learn state spaces with deep neural networks in such an active inference scheme? Well, basically, we have two components. One is the generative model that I rehearsed from the first slide, and we have our approximate posterior model. And basically, you can see that there are three parts in these equations. And the first part is basically the transition model. So it outputs the probability of your state given your previous state and the action you did in that state. Second part, oh yeah, and also the initial state is basically also part of the transition model, but then you just provide with a zero action, for example, just to bootstrap it. The second part is then the likelihood model. So given state, you want to have a model that predicts what kind of observation you will see. And then finally, you have the posterior model that, given the previous state, action, and your current observation, also has to predict which state you're, or also has to infer which state you're in. So basically, the posterior model has to come up with the same thing as a transition model, but in addition, it has access to your observation, basically. And again, similar to a transition model, to bootstrap this for the initial observation, you don't have any action, but it can be modeled by the same thing. And so all these three components, we basically instantiate these as deep neural nets, where they have to basically be trained to come up with these three models. So if we put it in a schematic, we basically have something like this. So given your state and action from the previous time step and the observation from the current time step, you on the one hand provide the previous state and action to your transition model, which will then output a distribution over the current state. And in this case, this distribution is basically modeled as a multivariate Gaussian distribution. So basically, the output of the neural net will be the means and the standard deviations of a Gaussian. And then we basically use this distribution to then generate samples for the next time step. And so the posterior model gets also as input the state and the action from the previous time step, but also, in addition, the current observation. And it also does a prediction on the current time step. And after sampling, you basically have the likelihood model that can then generate a prediction of the outcome. And then this state is put to the next time step, and the story repeats. And so, as I already mentioned, the output of each of our neural nets is basically some mean and standard deviation of a multivariate Gaussian with a diagonal covariance matrix. And we use the reparameterization trick to generate samples. So basically, we generate sample by having the means and then add the standard deviation times some standard normal noise. And this basically allows you to backpropagate gradients all the way through this neural net, also if you draw samples from the models. And then, of course, for the next time step, you just propagate a sample, and then the story repeats, basically. So training such a model is then basically first collecting the data set of action observation sequences. So you take your agent, you either let it randomly generate sequences in the environment, or in the case of a real robot, for example, you drive it around yourself in the environment while you record the actions and the observations. And while the models are not converged, you sample some subsequences from your data sets. You estimate the states that are visited and you reconstruct all the observations. And then you basically backpropagate the free energy loss. So this is the same formula as the free energy in the start. So on the one hand, you have the KL divergence between the output of your posterior neural net and your prior neural net. And on the other hand, you have this reconstruction error that basically scores how good you're reconstructing the actual observation. And using this loss function, you just update the parameters of your neural nets, and you basically build a model that is able, on the one hand, to infer your current state given your observation, that is able to generate new observations if you know which state you're in. You can reconstruct these observations, but also you have the transition model that you can then just use to, in the state space, plan ahead what would happen if I would do this action, and it will give you a distribution over the next state, basically. So then we come to the planning part. So once you have this model, how can you use it to let your agent do useful things? So there we will use Monte Carlo sampling. So one of the things, one of the limitations of these kind of architectures is that basically we only approximate the distribution for the next state. So given a sample from the previous state and given the action, we approximate the distribution for the next state, but then we sample during training as well. So we will never have like a good distribution for, let's say, 10 steps ahead. And so to predict then distributions for further in the future, we approximate these by doing Monte Carlo sampling. So for each of the policies we want to evaluate, we sample n trajectories that all do the same actions, but that due to the sampling might give us different results in terms of future states and observations. So for each time step, we then have a bunch of states and a bunch of predicted observations. We then fit a Gaussian distribution using the sample means and variances. And then we estimate the expected free energy as follows. So on the one hand, we have this KL divergence, if you remember, that scores how good your distribution of states is according to some prior preferences of states. So you use this Gaussian distribution to calculate the KL divergence with respect to these priors. And on the other hand, you have this entropy term that scores the ambiguity of these states. So here we basically use then the entropy of the observations generated in our trajectories. And we also added a scale factor rho to just kind of weigh the two terms from one another, which allows you to make an agent more risky, let's say, if it puts more weight on realizing preferences early. Whether you could also make a more cautious agent, let's say, that really does not want to end up in some ambiguous states. And crucially here, we also have kind of this recursive notion in here. So we do this rollout for k time steps ahead, and then for the future, you could kind of recursively look further into the future, let's say, and aggregate also expected free energies from that point. And to make it a bit more clear, let's try to visualize it a bit better. So suppose at some current time step t, you're in the state, then basically what you do is you use your transition model to say, okay, given that I follow policy 1, what will be the next state? And you draw a sample from the distribution. So this is then st+1 by following policy 1. And this thing you can repeat for k times. So we put in this k to just have some kind of some coarse grading of actions, let's say. For example, in the case of a driving robot, it might not make sense to switch action every 10 milliseconds, let's say. So if you decide to drive forward, you want to keep on driving forward for at least some time. So that's basically where this K comes from. So you follow the same policy for some time steps, and you basically sample this n times. So you repeat this process n times. So you have now at each time step n samples for the kind of states you think you will visit after following the first policy. And then if you have a second policy, you can do the same thing for that policy. So in this case, we only consider two potential policies. For instance, go left or go right, let's say. And then at this point, so at time step t plus k, we can basically repeat this procedure and say, okay, what if after k time steps I switch policy? Maybe I first have to go left and before turning right, or maybe I have to turn left twice. So then basically you repeat this process, and this you can basically keep on adding to the search tree for as long as your computation power allows you, let's say. So then how do we calculate the expected free energy from this? So we take our formula. So basically what we do is at each time step, we first use the likelihood model to also predict what are the observations that I expect in these states. And you then look at all your state samples from a certain time step. And this then gives you this approximated Gaussian distribution for both the states and the observations. So you plug these into the formula, and this then gives you kind of a number that says this is the expected free energy if I think I am in states t plus k, and I will follow along with policy 1 from thereafter. And then basically you can do this for each of these sub-branches. And this is then where the recursion comes in. So then we basically state, well, I assume that my active inference agent also at that time step will most likely choose the policy with the lowest free energy. So basically we combine the free energy for policy 1 and policy 2 according to the weights that are provided using the softmax function. So if if policy 1 has a very, very low expected free energy compared to policy 2, then basically only the expected free energy of policy 1 will be added thereafter. If they are kind of the same, then they will both have kind of a 0.5 weight, or if the other one is the clear winner, then it will mainly be the contribution of this thing. But so we basically combine these, assuming that your agent will at that point also select the policy with the least free energy. So now we basically have an estimate of what will be the expected free energy for the future, given that we are at time step t plus 3. And then we can further go up to 3. And so then for each branch, again, we will use the first part of the formula to estimate these Gaussians, to calculate the KL divergence and the entropy term, and then add this together with what we already had for the remaining part of the tree, basically. And this is very similar, I think, to what Carl Friston proposed in his sophisticated inference paper. So basically, at each step in the future, you kind of only consider the free energy of the branches that you think will basically be the best ones. So in the end, you'll end up with an expected free energy for both of your policies, and you then select the best one and start acting accordingly. So I'll now turn to Ozan, who will give some more details on the various experiments that we did that hopefully gives some more insights on how this can work in practice. So take it away, Ozan.
Yeah, hi. I have some echo on my end. Maybe it's resolved now.
Yeah, sounds fine. Thank you.
Okay. So I'll go briefly through our initial experiments. So that these are the experiments we did in like the past 1 or 2 years. And so one of the first experiments we did and reported on was the mountain car, which is a fairly well-known benchmark, I think. So the goal is to have this underactuated car, so it does not have enough power to reach the top of the right-hand mountain, but you want to reach it anyway. So ideally, your agent should learn here that it should first go back a bit to the left to gain momentum, to gain enough momentum so that it can climb the steeper mountain on the right. And even though this is such a low dimensional problem, it only has positions and velocities, it is actually a very interesting benchmark to experiment upon because there's no greedy solution. So any agent that just wants to realize its preferences immediately will fail at this because it will always fail to drive up the mountain. Now, for our experiments, we made it a bit more difficult. We made the fully observable mountain car partially observable. So what we did was we omitted the velocity information and only provided some noisy estimate of the actual position. So the agent actually had to learn two things. It had to learn, first of all, what its precise position was, and then also how this position relates to the momentum by its velocity. And then if we start from this setup and we train the model that Tim explained a bit earlier, in its most basic form, you can actually learn a state space that closely mimics these physical constraints of the system by minimizing energy. So if you look at the right upmost figure, you'll see that you see these sinusoidal state space dimensions, and these closely mimic the actual observations of the real world in the lower image. So as you can see in the lower image, we have the ground truth in green, which is the actual trajectory through its position of the cart. And then also our state transition model estimate. So our prior estimate on the position without observing. And then also in the blue line, which is a bit harder to see, you can see the same estimate, but now corrected with the observation. So it's actually just a posterior model outputs. And you can see these shapes returning in the state space, which in itself does not say that much, but it gives you at least a kind of vague idea that at least the state space is capturing something relevant for the problem. And I think there's one more animation on this. Yes. So yeah, it's the same conclusion. As I said, right now you can predict the future, as you can see in the orange line, and it appears to learn the velocity in its state space. Now, if you can go to the next slides. Yeah. Now we want to actually figure out how we can use this model that we learned for active inference. And typically in RL, you would give some sparse reward for driving up the mountain. But in our initial experiments, we were more interested in how an agent could learn from human observation demonstrations. So we recorded 5 human rollout in the environment, just like driving around with the cart. So you go first left and right. And then we push these trajectories through our models to get through our posterior model to get a preferred state distribution. So here on this figure, you can see the 8 different dimensions, how these evolve through time if you follow these trajectories. So, and the spread, of course, gives you the standard deviation at each time point for that state value. And then, if you use this preferred state distribution, and you calculate the G, or at this, or even only the KL divergence between your posterior and your preferred distribution for different trajectories through time. So here, every different color, every different trajectory is a different rollout in the environment, or imaginary rollout through the environment. You can see that you can actually use this preferred distribution to rank trajectories according to lowest free energy. So you see that the blue curve is the only one that reaches the top, and is also the one that the model seems to prefer. Then in the next slide, yes, we experiment a bit what this means in terms of the actual free energy, so also compensated with the entropy. And what we did here was we had the agent observe the world for one time step. So we give it an initial observation to get a sort of bootstrapped latent sample. And then we will only use the prior model to imagine what will happen if you follow certain policies. So here we considered 3 policies, or like 2 possible policies that you can switch at 3 time steps. So you either go left, right, right, left, right, left, etc. Or you can start with right, and then these are the blue curves. And what we see that if there is no initial velocity, then you see that the agent imagines that the optimal policy, which is left, right, right. So first go as far up left and then just blast your way to the top, gives actually the least amount of spread. And also he believes that this will reach the top earlier than any other policy. Inversely, if you look at the policies that first go right, then you see that there's still a little, there's close to no spread due to the lack of initial velocity, but the agent already knows that it's impossible to reach the top. Now, if you go to the next slide, so here we do the same experiment, but we add some random initial velocity. And again, we let the agent observe the world for one time step, and then let it plan according to the same policies as before. And first of all, you see that the agent has a much larger spread on its believed outcomes. This is due to this extra uncertainty on what the initial velocity is. And also, this initial velocity might render previously infeasible policies feasible, as you can see at the bottom, because now if the agent thinks, yes, my initial velocity is high enough, even with the one of the more suboptimal policies, it might still be possible for me to reach the top. And if you go to the next slide, please. Here we can then see this in action. So this animation, we collapse the imagined trajectories to the actual trajectory. And you see that in the beginning, if we can maybe play it again, in the beginning, it believes that more red policies will reach the top. And then as it gains more momentum, it will believe that all blue policies will reach the top. And even it will know that if I now go left, so I decelerate, then I will less likely reach the top. So I think, yeah. So as you can see now, he knows that red will not reach the top. And yes. Then another experiment we did building upon this was, what if we take this same approach, but now we move to the kind of problems we want to solve. So the high dimensional observations that you cannot model by hand. So we took another OpenAI gym environment, the car racer. And here the goal is to drive the red car, as you can see on the high resolution image on the left, on the road for as long as you can. And then we trained our model on a handful of human demonstrations of this. And then you can see that in the reconstructed image on the right, it's even on a handful of observations that can learn to predict this. So we did exactly the same thing as before. And I think this is an animation now. Yeah. So if you then use the planning tree that Tim explained on this little card, it will have learned that the road, so the gray area, is important, and it should stay on this. Now, this agent is a bit more greedy since it tries to shortcut corners to get quicker on the gray part, as you can see here. Okay, if we can go to the next slide, maybe. So now, and also an important point here is that our active inference approach, which is model-based, seems to be a lot more data efficient. It seems to be a lot more data efficient than, for example, a baseline RL agent. So we took DQN, since this is also an off-policy algorithm, to be able to compare it kind of similar to our approach. And as you can see in the first graph, so for the mountain car, our model quickly, our models are is the orange. Our model quickly learns that at least some method to reach the top, and then afterwards it just improves upon this. Whilst due to the sparseness of the rewards, DQN is not able to learn as quickly, and even after having 1,000 times more observations, it still isn't capable of climbing the mountain. And even for the car racer, it's even worse. So here we trained on 7 or 10 rollouts, and immediately we're able to get a reward of 600, whilst DQN just fails to get that same level of performance even after 1,000 rollouts in the environment. So if we can go to the next slide. Yeah. And then a final experiment I want to discuss today is the robotic navigation, or like maybe more accurately, robotic control. So here we took our KUKA platform and we mounted some sensors on top of it, and then also put it on a laptop for good measure to have some compute. I don't think the sensors are really relevant for what we're going to discuss now. So then we drove around with the robot in our lab, as you can see on this movie, just like with the joystick, and captured a lot of data. And we just drove up and down the aisles with the robot. Now, this environment is also a bit challenging for robots since all these aisles are super similar. Like for a robot, knowing if it's in aisle 1 or 2 is nearly the same thing. It's very difficult to comprehend for the machine. So then in this slide, you see what a recording might look like. So you have LiDAR and radar feed and some images. Yeah, sorry, Tim. This is now the correct slide. And then the goal is to, again, train a model that will be able to generate future observations for the robots. I don't know if there's an animation on this slide. So yeah, so you saw the high resolution image was the real observation. And this is then what the model thinks will happen if the robot first turns right and then continues to drive. The little ghost artifact you saw a couple of frames ago. So yeah, we'll first look at it again. So we drive, and then it will turn, and suddenly you will see a ghost Tim appear. This is because the model doesn't actually know what will happen. It can only try to guess based on its previously learned experiences in the model. And there's a lot of people walking around in the data set. So there was some chance that somebody would be walking there. So it just might imagine that there's somebody there. Then maybe if we go to the next slide. This is also an animation. So here you can see, for example, how these imaginary samples deviate. And this is also the reason why we need this sampling. So the different sampling in the planning tree for different outcomes. So you see that given the same starting position and observation, the model learns that turning left might have different outcomes depending on where it is in which aisle it is and where it is in the aisle. For example, the top right, then the robot imagines that it is at the end of the aisle, whilst in the bottom 2, it imagines that it is in the aisle, so it just imagines some stuff on the racks. Then here is then how we can evaluate policies. So we provided 3 possible policies: turn left, fourth, and turn right. And then you can imagine what all these things will do in the environment. And then similarly as before, you can calculate the G and select the one that will most likely bring you to your preferred sequences. Yeah, right. Sense of fusion. Also, the nice thing of our model is that you can because it's a neural network, you can put multiple types of observation into your posterior model. You can fuse them in various ways. So what you can see here is that similar to the camera feed, the robot will also learn the effect, for example, in a LiDAR scan, and also it will learn the effect on the velocity bends in a radar scan. And this gives you, of course, extra robustness in your planning because you can now reason on multiple modalities. Then maybe in the next slides. There are, of course, still some limitations to doing robotic control this way. First of all, our robot is extremely short-sighted in time. It can only learn to predict as far as the length of the sequences we provided during training. And also, the longer you roll out, the larger your search tree becomes, the more computational limits you will reach. So this is also then an area we're now actively working on. Then currently our models still require that we pre-record the data set. So our models require that we drive around ourselves and then fit the model. So there's also a point we're currently at this moment working on. And then tying into this, our models currently do not really know how to explore, whilst there's probably a sensible way to do exploration based on the free energy principle, since your model uncertainty can be baked in. I don't know if we have any more slides actually now.
No, this is it. So maybe it's good time for questions.
Awesome. You can unshare and we can ask some questions. So I wrote down a bunch of stuff, and also anybody who's watching live, please ask some questions. So nice presentation though, and awesome, very instructive videos. Hopefully made us think, made us laugh a little bit when it cut corners. So maybe just a starting question while people are writing their question. What brought you to be studying this topic in this way? Were you coming from active inference and saw robotics as an interesting application, or were you in the area of robotics and then found active inference to be a useful model?
Yeah, so basically we were in the area of robotics and reinforcement learning, basically. And we were working on building better low-dimensional state representations to feed into a reinforcement learning algorithm, let's say. That was our initial idea. So just building representations for better reinforcement learning. And then we stumbled upon the active inference framework, which basically not only gave us a way of how to build these generative models, because basically we found ourselves the free energy of the past, that we were basically already doing that, but we saw that it also gives us, in the same mathematical framework, a way of how to project these things to the future and use these for planning, for resolving ambiguity, and also for scoring novelty, and all these nice properties that are basically lacking in RL. So that's why we basically started digging into this mathematical framework to go through all the papers of Carl and see how all the ends are tied together, and see whether this would still work if you don't have your state space defined upfront, but you just learn it from data. So that's how we started this endeavor, and that's pretty much where we are at this point, and still investigating it further.
Awesome. That was gonna be my second question was like, what differences or advantages would you describe for active inference over reinforcement learning or other machine learning frameworks? If you answered it in previously, that's great. Or do you want to add any other thoughts?
Yeah, I think the nice part is that you automatically get the nice properties of resolving ambiguity and of potential exploration if you also estimate posterior distributions over your parameters, for example. So these are very interesting properties mathematically. However, it's still there's still a gap to actually get these out of these real world cases if you don't have the generative model predefined, let's say. So there are still some challenges, but the theory at least is very much appealing. But I think if you look at what's going on at the RL side, at reinforcement learning side, then there's not that big of a gap between the two fields, I think, because you look at all the curiosity bonuses that they tried to come up with in reinforcement learning, and if you look at the model-based stuff from like Daniger Hafner with his Dreamer approach, then everything is kind of similarly converging to it's a good idea to build a model of your world and get more sample efficiency, and it seems like a good idea to have some planning in there, and maybe there is some gain in curiosity, and so you see that in a lot of different independent research tracks, we all converge along the same lines, and I think what is so appealing to active inference is that basically brings this all together from a single principle, which makes it a very nice framework to work with, I think.
Anything to add on that, Ozan?
No, yeah, I was, before Tim mentioned it, I was already thinking along the lines of the work of Denisha Hafner. So, I mean, if you look at his models, and I think that is currently almost state-of-the-art in model-based RL, then you'll find that the models they are building are very similar to the models we are building or other active inference researchers are building. So, yeah, I mean, it makes sense that all these approaches converge on a single idea if the idea works.
Yep. Very interesting that like plan to dream and dream or imagine so that you can sample appropriately. Why put that as a second layer on the model or have to incentivize it in a sort of ad hoc way? Why not have that be the basis of the model? So that's a very nice point. So Dean in the chat asks, have the authors heard of the Missionary and Cannibals game/problem, which is moving two kinds of mutually incompatible agents back and forth from two sides of a river? And if they have heard of this or thought of any kind of analogous cases, do you see any applications?
Yeah, I haven't heard of the game before. I think it's probably similar to the like crossing the river with a chicken, a fox, and a goat, or what
Yes.
was it?
Yeah, there's like animal versions. There's all kinds of versions of this one. But going back and forth with different kinds of incompatible agents, and you need to sort of go to the left before you can make it up the hill, but it's a little bit of a different setting. So what does that make you think of?
I hadn't actually really considered it for our models, but it might be if we find a way to model it in an environment and then maybe collect some data on it.
Yeah, I think this is a problem that is very nicely suited for doing it, let's say, the vanilla way, where you basically write out all the different states that can happen and kind of observe the outcomes that you can have. So I think you could actually formalize it in such a way and then run an active inference simulation on that and see what happens. So that's less of our interest, because in our cases we are mainly interested in what if your observations are so high dimensional that you cannot even start thinking about writing out the generative model, let's say. And the only thing you can do is interact with your environment and try to learn it from the data, which is slightly different take on the active inference problem, I think.
Great. Another question is, you are all deploying these models sort of real time with physical agents, embodied agents. So what surprised you, or what was interesting to note as far as going from the simulation only, where you can sort of put everything in a box and know exactly what's going to influence what, to the world of embodiment, where, I don't know, some dust could get into the robot, or I saw a person walk by. So what comes into play when you actually deploy physically, and how does the model deal with that?
For me, it's actually the thing I like. Well, first I played around a lot with the mountain car and the car racer, but the first thing actually was a real hurdle for me personally was deploying it on a real robot. You suddenly have all these hardware constraints. Like don't have infinite memory, you don't have server grade compute anymore, and you have to fit it. For example, I think Tim and I spent a lot of time to make a demo working where we could roll this out real time. And just the hardware constraints of doing something as complex as active inference real time on a real power constrained robot is another challenge in and of itself.
Yeah, so I think if the question was what do you get from doing it on a real system, well, a lot of frustration and pain, I think, is the answer. But likewise, if it then works, then the gratitude the satisfaction is so much higher. So I still remember Ozan and me cheering in the lab because we gave the robot a preferred state of being like nicely in the center of the ale, and it was actually moving along the ale, and then at the very end it decided, this is not the center of the ale anymore, and it just made a 360-degree turn and started driving back, and we were like, oh, this is awesome. So I think there's lots of pain and frustration to get it work, but then once something comes out, then the satisfaction is so much higher than when you see a mountain car reach the top.
Interesting. You could set up a physical valley, maybe make a physical mountain car, because there's so much comparison of the software realization, but maybe that would be even taking it to the next level. So another thing that you talked about repeatedly, maybe even in every example, was actually training the model from just a handful of human cases. Like you drove the car, you had people play the mountain car game. So what exactly is happening there, and how does the model like not overfit to the few trajectories you show, or not just say, hey, you only gave me 3. What's the deal with these 3 totally different trajectories? Like what exactly is being learned or updated in the model when you provide just a handful of human examples?
I thought Tim was going to answer this one.
Yeah, So basically, I think overfitting is clearly an issue. You're no matter what you do, you're constrained kind of to the data you provide to the model, so it cannot really learn anything else than what it discovers. So that's also what we pointed out at the last slide. It's a severe limitation of our current work, clearly, but there is there is no other way when there's a real robot involved to get started, let's say. So that's the easier way to get started. So that's mainly the driver. But at the moment, we're actually working both in simulation, but also on real robots to see, can we actually get these systems to decide how to gather their own experience, what is interesting to learn from, because that's actually one of the, to shortcut to one of your previous questions, what does active inference give you? Well, that it actually can deal with these kind of things, like my robot needs to collect its own experience. What will it do? Will it do always the same, or will it explore, or these kind of things? So these are really some active areas of research. But then, so to come back to the overfitting problem, so one thing that mitigates overfitting a bit is that the fact that you have all this stochasticity in the system that you constantly sample states, which makes it a bit more, but it's not like a classifier that overfits to the test set, let's say, there's always some kind of noise in there. But you're right. It is, in some sense, overfitted to the data in the sense that it cannot predict scenarios that it clearly hasn't seen before. But so one of the nice things of having this this expect free energy formulation is that you actually punish your planning with this entropy term, which basically means that if you plan ahead in some space that the model wasn't trained on, then typically you will have some more variation, some higher entropy for that area, because typically your observation becomes very bad or very blurry or out of distribution. And so in some sense, the model is kind of robust against that. And it will also, if you then deploy a policy or like do the planning, it will kind of try to stay close to where the model, to the regime where the model was trained, okay, because there you basically get the better predictions. So in some sense, that also mitigates the problem.
Also, I want to add that we could use as little of the rollouts as we did, because actually, if you had let a human do the rollout, you solve the exploration problem for the agent. You already get a very good coverage of the relevant, feasible state space. You get, like, for the car racer, if you let a random agent drive around as exploration, 99% of your data will just be grass, and the agent will learn nothing about roads. So by having a human drive it, you know, okay, this is a road, and apparently this is important because it's in every observation I've had.
That almost makes me think of two ways that we're seeing these large models be trained, with a sort of mentor, like a human who says, you know, here's the first places you want to be sampling. Here's how you drive the first time. That's the driving instructor side by side. And then there's the generative adversarial approach, which is just the almost opposite. Like, we're going to be passing the model the most confusing possible data. And so it's sort of like with this carrot and the stick, or the push and the pull, these models from both of them, maybe one or maybe both, they figure out how to be on that razor's edge. And then in the race car example, it was cutting corners. So that just made me wonder about autonomous vehicles. And you say, okay, well, the goal is to stay on the road and to get there fast. But then sometimes get there fast is going to take priority. And then all of a sudden you're way off the road, and maybe now your car is ruined or something like that. So if these were to be deployed, like, how will we even know what kind of preferences to instantiate the model with?
Yeah, and that's a very good point, in fact, because how nice active inference might look in theory, I think it's not a silver bullet to autonomous agents, because a lot of the subtlety is still in how do you provide it with, like, the preferred prior distribution, and that will be crucial in a real world system of it's similar to a reward. Basically, it's a bit more informative than just a scalar reward signal, let's say, but it suffers from the same issues as in if it gets a way to shortcuts to get this preferred state that you didn't envision before as a designer of the experiment, let's say, it basically has the same issues as reinforcement learning. So I don't see it as a silver bullet of solving autonomy, but at least it has some turning knobs that you can use to at least avoid some cases, like avoid these ambiguous states, or at least make it first learn the model properly. So it has some nice properties, but it's not a silver bullet to solving autonomous systems, I think.
Anything to add on that, Ozan?
No, I think Tim said it very well.
yes, the model is not a silver bullet, definitely recognized. What areas might be interesting shooting ranges, first applications where we can at least explore it? Are those the same use cases that people have been talking about just more broadly in terms of autonomous vehicles, or might there be a sort of division of labor where active inference is going to specialize like in those ambiguous scenarios? Or I just was curious about that. Okay.
So
Yeah.
yeah,
Go.
no, I was also still thinking, but like for us, I think the real next application we're targeting is just still the constrained navigation in, for example, a warehouse where the impact of misplanning is still fairly limited. So actually, more realistic versions of the situation we have in our lab, maybe. There's also the trajectory we're currently still on. So I think we still believe that there is some value in developing autonomous active inference agents for this more industry-like settings where you can at least separate it from general public and where you have also some level of control of the environment.
Yeah, I think it's similar to mitigating the same problem in reinforcement learning. Is basically that you before you just let the system randomly pick actions or pick any action at once, you kind of or an environment where at least as a human you can shortcut the system and say, okay, you want to drive forward into this rack, that's not a good idea. So you have at least some ways of defining some rules to keep it within some safety range, let's say. And within this boundary, it can, for example, move autonomously. But still, then you might have the nicer properties of the active inference agent that if you're driving around in some aisles and somebody just dropped off a box in the middle of the aisle, it will not freak out because the SLAM map is no longer consistent with how the robot was programmed, for example. But we just say, okay, this is another case. Either it experienced this before and it has in its world model an idea how to cope with this, or it will just be intrigued and start learning about this new situation. So I think these are then the nice properties you have in this agent, and you kind of bypass the all. It's getting too greedy to realize its preferences, because you kind of shortcut these situations by having this more rule based system in place that kind of limits the choice of action in this case.
Thanks for the answer. Here's a question from the chat. As the code is not disclosed, would you say sticking to what you write in your paper is sufficient to reproduce your results, or are there any further tricks you use in designing and training the models?
I think the art. Sorry, go ahead, Tim, first.
Yeah, I think that together with the appendices, it should be sufficient. What do you think, Ozan?
Well, I think we had some experience where I tried to help somebody out who was trying to replicate our results. I think we had some tricks for the planning. Like that isn't as straightforward to replicate, but the model prediction part, we explained the architectures and I pretty detailed in the appendices. So I think, and we don't do any extra tricks, for example, on data processing or our loss terms. So these should be easy to mimic, but I think the planning is a bit more involved, as we sometimes ourselves have difficulties replicating it.
Planning is hard.
Yeah.
Okay, if anyone else has questions in the live chat, they can type that. Another piece that I thought was really fascinating in the mountain car example, at least, was how you talked about the noise allowing for the previously implausible policies to become possible. Like we saw a broader spread of the trajectories when there was noise. How how is that being like integrated in real time, or how are the noise, which are often very small, how does that change the model's understanding of where it can go and what it should do?
Yeah, so in the mountain car example, there are basically two sources of noise. Let's say one is on the noise on your observation that you get. So you get a noisy estimate of your position. And so this is typically not so large because yeah, you need to have a sufficient signal to noise ratio just to learn anything, let's say. Um, but the second part was whether your agent starts with a zero velocity or with a random velocity. And these are basically two separately trained models. So either you have an agent always starts with a zero initial velocity, and then basically the model learns that the initial observation has zero velocity, and it basically knows how to properly predict from the first observation on, let's say. If you train the model where the agent constantly has a random velocity, then it basically learns, yeah, from the first observation, still a lot of options can happen depending on my velocity. And the more observations get in, you see how the model kind of picks up, okay, this is now my velocity. And from then on, you see how the wide range of options collapses to the most likely ones.
Anything on that, Ozan?
Well, I was just also thinking, for example, in the robotic planning example we gave, there you also see this spread, but then it's more as in that the model learned that at similar state values, different outcomes are possible. So it will try to maybe make the Gaussian in the latent space a bit wider, so that if you sample from it, you might get a slightly different sample value, and that will then generate the different outcome you want to visualize. So that's also, so even though the standard normal you're sampling from initially for your reparameterization trick is just standard normal, the model can learn to inflate or deflate this distribution so that you get a wider coverage.
Yeah, for example, what you also saw in the navigation example is that basically the model, since we train it on pretty short temporal subsequences of like I think 1 or 2 seconds in real time, so it's not able to have a very consistent prediction for longer times frames than that. And also, given the fact that every ale in the lab looks very similar, it learns the general structure, like there are racks left and right, and might be boxes, or you saw that kind of the boxes or the stuff actually in the racks is kind of very blurry, and it's kind of brownish, blackish, but there's no real, you don't really can identify what is in that rack, for example, and it has basically no spatial awareness of where in the rack, where in the ale am I? Am I at the very end or in the beginning or in the middle? It has no idea, and that's why you saw if you then say, okay, turn right for a certain amount of time, then it will either predict I'm in the middle, so if I turn 360, it will still be ale after me, or I'm at the very end, so if I turn around, I will see a wall. So it basically has no consistent knowledge of where it is, and so this is basically modeled as kind of noise in the distributions, and if you draw different trajectories, it will either think it's at the wall or it's facing the other ale, or there's a human passing by, so I see some shady people-like structures. So all these kind of things are then modeled as kind of noise in your distribution that just appears to be happening there.
Makes sense. What might be helpful or required for long-term planning? Because the tree that you had with the multiple, I guess, bifurcations or whatever they represented, that was very interesting. How you had a very fully fleshed out tree, and then you showed kind of how you recursed to prune back down to make a policy selection. So as you suggested, that exponentially explodes the computation. What might be helpful, or how can long-term planning be achieved with reasonable hardware?
Yeah, so the key thing here is hierarchical models, I think, and that's what we're pushing very hard on now. Is basically that you, given a model like we trade now, you basically put a new model on top of that now as observations does not get pixels, but it gets state samples from this model basically. And the time step now is not to predict the next time step ahead, but like to predict 10 time step ahead or 20 or whatever, or however you want to coarse grain basically. And once you're at that point, then you have basically a system that can plan. If you plan 10 time steps, you're actually planning 100 time steps for the lower level model. And so this way you can keep on coarse graining that you only have to explore a few policies at each level. And then down below, again, you only have to predict for like 1 second ahead because the other plan was made by the models on top. And so this way you can easily bypass and scale down the complexity of the planning procedure.
It reminds me a lot of driving, where it will be like, okay, in 5 streets, take a right turn. So you're not pre-saging the right turn until, okay, 1, 2, 3, 4. All right, now I should get ready. What about symbolic information? Like, what if the aisle had a color gradient, or if it had 1 dot, 2 dot, 3 dot? Could that be learned in an unsupervised way? A symbol in that pixel level model, or is that where a hierarchical model would come into play?
Well, I think the problem currently is, for us, architecture-wise, our model isn't capable of capturing very low-level details about the environments, just because we are based on a VA approach, and then the mean squared error objective we use for reconstruction and the way we sample is already inhibiting, for example, recognizing dots in your inputs. Maybe, actually, I don't know what Tim thinks about it, but I think color gradients is something like the model might learn if given enough data and incentive.
Yeah, so I think there's a number of problems with the approach in the sense that we're now doing prediction in pixel space, let's say, and the way you calculate the likelihoods, you evaluate the likelihoods and you calculate the reconstruction error. It basically means that you want to have each pixel independently predicted on average quite right, which means that if you have very fine-grained details, it easily ignores these. You also have the complexity term that basically says, okay, I want to have the least complex representation for reconstruction. But this basically also means that depending on how much you put pressure on restricting the complexity, the less information you will actually encode, and the more blurrier basically your reconstruction will become. So it's very similar to the beta VIE, for those familiar, where you have this beta parameter that tunes how much weight you put on the GAL divergence term versus the reconstruction term. And this also has impact on what the model will actually put in the state representation and which details will be ignored. So yeah, I think a lot of these things are very difficult for the model that's straight now, just because the way we built and parameterize the likelihood model.
Very interesting. How might somebody go about learning or exploring this? Like, is there a textbook or the citations that are in your paper or hands-on? What would you encourage somebody who is curious about this and wanted to, over the next maybe few years, be following?
Yeah, I mean, we had a lot of, like in the active inference part, I think when we started out, there wasn't that much information on how to do active inference. So we had to figure it out the hard way by trying a lot and failing a lot. But now currently, I think even in this model stream, there was some cool information and accessible information on active inference. So, and I mean, specific implementation wise, if you want to build a model like this, I think the current state of the art in RL and active inference, or learned active inference is all pretty similar.
Yeah, I agree. So a lot of things have changed regarding how accessible the information on active inference has become. If you look now at the tutorial from Ryan Smith, for example, which was also extensively covered in one of your videos. So I think that really lowers the entry bar to just get to know the theory and how everything works or should work, and to play around with some small toy examples and simulations that you can get some insights on what does this thing do and how does it work. For the deep learning part, let's say, to build these models, then probably the resources to go to are just like tutorials on variational autoencoders. I think these are the things in deep learning that are most relevant for the active inference work we discuss here. And if you can build a variational autoencoder and you know how active inference work, and you put the two together with some details from our paper, for example, then I think it should be pretty straightforward to get to the first working example.
Cool. Any closing thoughts or even questions for our lab, or just to leave for people to be thinking about as they dream in preparation for action?
Yeah, maybe I just want to continue a bit on what Tim said earlier, that, for example, if you want to build hierarchical models, you don't have to build an active inference model on top of an active inference model. We did some preliminary experiments on, for example, just using our active inference model as dynamics model for a SLAM algorithm. And then you also already get hierarchical modeling and some of the long-term benefits. So maybe that's also interesting, like, to think about, is how this active inference model fits in already existing techniques.
Yeah, so I think what Ozan wants to say is that in this case we use like these deep neural nets to parameterize this transition model, likelihood model, and posterior model, but you shouldn't always revert automatically to these deep learning techniques. So these are kind of very popular right now and very cool, but in some cases it might be sufficient if you know your environment. Then yeah, you shouldn't bother learning the state space model. If you know the state space model, just use it. I know we used the mountain car example here. So this would be a good example of why we shouldn't just use the deep learning approach. This was basically just to have like a proof of principle for us to get some simple example working. But it only pays off, I think, if you have like these real high-dimensional observations, and you have no clue how to parameterize your state space model. But it's not that this is like the default way to go, let's say. And we're also like kind of evolving, especially as also said, if you move to these hierarchical models, then we're kind of looking at how can we make a more kind of discrete style parameterized state space model on top, where we basically try to cut the whole state space into discrete parts and then have like a simple transition model. Like you gave the example yourself, Daniel. If you think about navigating yourself, you're not thinking about predicting all the pixels of all the houses, but you just think about, I need to go forward now, and then the second street to the left. So you basically chunk up the whole continuously state space into some relevant parts. And then your transition model also becomes like a very simple matrix with transition probabilities. So I think the future is in hierarchical models, and the future is in a mixture of some learned parts, but also some very discretized, intuitively comprehensible parts.
Just 2 points on that. One is something that's always drawn me to active inference is that it's inference conditioned and about action. So you're not going for that 4K Google Street View, what does every house look like? And again, when that's the input data, even if you have a generative model, that's the output data. So active inference is a really principled way to just sort of reduce what you're predicting to like, which way should my elbow move? Not what will the pixels look like when my elbow moves, which may be just taking gigabytes of data. But if it's just reduced to the state space, then it's easier to learn. And that's why it was such an interesting contribution with your paper to actually learn that state space in the context of high resolution and real time and heterogeneous sensors. And then also it's something that we've seen many perspectives on in the lab and in these discussions is there's the philosophical discussion, map and territory, who's really an active inference agent? Is it everything, a dust particle, a bacteria, is the world built this way? And then there's this sort of engineering approach where you have your preferences for how you want to see the robot work, and then whatever you can tinker and cobble together, that satisfies you. And it reduced your uncertainty about performing the task you're trying to perform. So it sort of sidesteps, but then it sidesteps those questions in a way that actually brings us to a higher level of understanding. Because I know that many listeners who are not as advanced in the machine learning will be inspired and have qualitative thoughts based upon what you brought here today. So thanks again for this awesome presentation and conversation. And we'll always appreciate hearing any follow-up whenever the time is right.
Yeah, thank you, Daniel, for having us. It was
Awesome.
really nice discussion.
Okay. Peace. See you later.
See ya.
Bye.
Bye.